I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will discuss the topic NAND and NOR implementation for the course Digital System Design. So in the previous video, we have discussed the logic gates. A logic gate is an electronic circuit which makes logical decisions based on the combination of digital signals present at its inputs. So there are so many logic gates are available, but the most common basic gates are AND gate, OR gate, and NOT gate. The inversion of AND is NAND, the inversion of OR is NOR, and inversion of XOR gate is XNOR. So these are the common basic gates available. And in all these gates, the two gates NAND and NOR are called as universal gates. So a gate that can be used to create any logic gate is called universal gate. As I said already, NAND and NOR gates are called as universal gates because they can perform all the three basic logical functions OR, AND NOT using these gates. And now we are going to see how to implement the basic logical functions and also any type of function using NAND and NOR gates. So now we are going to see how to get a NOT gate and also AND gate using a NAND gate. So a NAND gate with single inputs acts like a NOT gate. So in the first diagram we are getting NOT gate from the NAND gate. So NAND gate inputs, two inputs are combined and it is given as a single input. So this type of arrangement gives a NOT gate output. And next is the NAND gate. So we know the complement law. So if we take the variable double times the complement, it gives the original value. For example, if we have a variable A, if we take 2 times the inversion, A double bar gives the original value. So in this way we can obtain the two NAND gates simultaneously and we got a original function of AND gate. And now next is NAND implementation of using OR gate. So now we are going to obtain the OR operation from the NAND gate. So in order to obtain this, we use two inverters at the input of the NAND gate. It gives the performance of OR gate, and this is based on De Morgan's law. And this diagram is symbolic equivalence of NAND gate, 3 input NAND gate. Either we can give bubble at the output side or at both the 3 inputs we can give the bubbles, and its first diagram operation is XYZ the whole bar. Second diagram operation is X bar plus Y bar plus Z bar, and it is also equal to XYZ the whole bar. And now if we take a function f is equal to ab plus cd plus e, and how to implement the Boolean function using NAND gate, we are going to see in this example. So for the given Boolean function, in order to get AB we use AND gate, CD we use another AND gate, E is directly given. So this the mid function is the OR function. So we are giving all the outputs to a OR gate to obtain the original function f. So using NAND gate we can also obtain the same results like this. In the second diagram we use 3 NAND gates. So the output of 3 NAND gates is given to a single NAND gate, which gives the original output as we obtained in the previous diagram. And also the third diagram gives the same result of f is equal to ab plus cd plus e. So in this, the 3 outputs of the second diagram is given to a 3 input OR gate. So this also gives the same function f is equal to ab plus cd plus e. So in this way we can implement any Boolean function using only NAND and also NOR gates. So this is 2-level implementation of NAND gate. So next we are going to see how to get the basic gates using NOR implementation. So for example, take an AND gate. So for getting an OR implementation of this AND gate, we use two inverters at the input side of NOR gate. We get the AND gate output. So the activity, and now we are going to see how to get OR gate from the NOR gate. So for get OR gate, we have use complement law. So we take 2 times the NOR gate, the output is the original gate OR gate. And using De Morgan's law, we can write the graphical equivalence of an OR gate. So first diagram, the graphical representation of an OR gate is drawn for x plus y plus z the whole bar. Second diagram is drawn for x bar, y bar, z bar, which is also equivalent to x plus y plus z bar. So here the bubbles are given at both the inputs individually for the NAND gate. So the same two-level implementation, now we are using NOR gate. The function taken is AB bar plus A bar B plus into C plus D bar. So for this case, for AB bar we use AND gate, A bar B another AND gate, and also next is C plus D bar we used. So here A bar B bar NAND gate is given to another NOR gate, AB is given to another NOR gate, and similarly CD output from the NOR gate is taken, and all these outputs are given to NAND gate, which gives the original function. So assessment questions, universal gates, we know NAND and NOR. These are called so because any gates can be implemented by using these gates. De Morgan's law, we have seen there are two laws. A plus B the whole bar is equal to A bar into B bar. AB the whole bar is equal to A bar plus B bar. And in the previous examples, so far we have seen, we have explained the implementation of any circuit using universal logic gates by using De Morgan's theorem. Thank you.